I'm very pleased to be here, to make this this keynote. And my talk, is an overview about, a series of problems that, civil engineers can face today, and which is called, dynamic interaction or dynamic coupling. It is not new to say that, since the past 30 years, a lot of work has been done for introducing structural dynamics concepts into design purposes. This is mainly due to the fact that more and more slender structures are built today than before, and consequently it is quite important to take into consideration time-varying characteristics of the loading pattern and in an efficient way. This is why, in fact, the process to move from statics to dynamics, we can say, has been quite successful. My talk today is more about another kind of process, which is, in fact, to move from actions to interactions. Before to go further, it's good to have an explanation about, this problem of interaction. And maybe the simplest example, I can give is a bridge-train interaction. Usually, railway bridges are designed by static analysis. But when you design high-speed track, you have, in fact, to take into consideration and to introduce more sophisticated analysis, and especially, to make a strong dynamic analysis. Because the objective is, in fact, to avoid the risk of resonance phenomena. Resonance phenomena concerns, the loss of wheel-rail contact, but also the destabilization of the ballast and, the exceedance of the stress limits. So you see, it's not only a problem of structural safety, it's also a problem of serviceability. And if you go back, to the first design of the high-speed tracks in France, the historical line between Paris and Lyon, several problems were met because on short-span bridges, cracks in concrete, high ballast, and big track irregularities, because, in fact, there was some resonant effects between trains and the structure itself. This is why, as you can see here, several strengthening measures were introduced in order to change, the dynamic characteristics of this bridge. Because, in fact, structural safety is not only the only concern, but also the serviceability of the track, it is necessary to combine structural dynamics with vehicle dynamics. So the flow chart, which is, on this slide, show that if really you want to have a good assessment of the serviceability aspect of your structure, you need, in fact, to model the vehicles and the suspension of these vehicles. You form the train, and after you can make the train crossing the bridge, and you can calculate the response. You can calculate the structural response, but you can also calculate, some criteria regarding, for instance, the loss of contacts or ballast destabilization. So you see, in fact, if you want to have a good understanding of the serviceability of your structure, you need to combine two systems. One is made by the train itself, and the other one is made by the structure. And when you combine two systems, it means that, in fact, you cannot analyze, one system without analyzing the other system. And this is basically what we call coupling. So let's go further, and let's try to give some basic definitions regarding coupled systems. What are exactly coupled systems? The simplest definition I can give is, in fact, that these are mechanical structure or subsystems coupled by linear or nonlinear properties. This is a case I presented, vehicular loads on bridges, but you can have more sophisticated problems such as stay cable dynamics. What is a bit more complex is that, the coupling can be also done by other physical systems based